Most calculus textbooks open on day 1 with the definition of the limit and then move on like nothing strange just happened. I want to do the opposite. I want to sit with this idea, because it took working mathematicians close to 200 years to pin it down, and the version your textbook hands you in a single boxed equation is the end of a long, bitter argument. Limits aren't a side topic. Every derivative is a limit. Every integral is a limit. Every infinite series, every partial derivative, every improper integral, every multivariable result you'll touch later in this course, all limits in costume. So we're going to do this slowly. The definition, where it came from, and 2 worked examples that show what the thing actually does. 2 questions sat unanswered for roughly 2,000 years. Greek geometry couldn't crack them. Classical algebra couldn't either. The first one, drop a stone out of your hand. You can time how far it falls in 1 second and divide, and that gives you an average speed over that second. Fine. But what's the stone's speed at the exact instant it leaves your fingers? Average speed needs an interval. An instant has no interval. So the question is either gibberish, or it's asking for mathematics that didn't exist yet. The second question is about area. Archimedes wanted the exact area under a parabola, and he got the right answer. He packed the region with finer and finer triangles and added them up. The answer was correct. He just couldn't say, with a straight face, what it actually meant to add infinitely many triangles together. Notice these are really the same problem wearing 2 different costumes. Compute something on a small but honest scale, then squeeze the scale down and see where the number goes. That squeezing operation is the limit. Calculus was invented twice. Between roughly 1664 and 1675, 2 people who'd never met built the same machine. Isaac Newton was holed up at the family farm, Woolsthorpe Manor in Lincolnshire, waiting out the plague closures that had shut Cambridge. There he developed what he called the method of fluxions. He pictured quantities as flowing through time and asked for their instantaneous rates of change. To get a number out at the end, he introduced a small quantity he called little o. He treated it as non-zero in the middle of the calculation because he needed to divide by it. Then at the end, he set it to 0 so it would vanish. Hold on to that move, it matters in a minute. Across the channel, Gottfried Wilhelm Leibniz, working in Paris during his years as a diplomat, arrived at the same machinery with much better notation. The dy over dx you write today for a derivative is his. The long s for the integral is his too. They got the same answers. They almost certainly did not steal from each other. That didn't stop their followers, and eventually, Newton and Leibniz themselves, from spending the early 1700s in a vicious priority fight that poisoned British and continental mathematics for the next century. The piece that matters for us is simpler. Neither of them had a real definition of what their infinitesimals were. The sharpest critique of early calculus didn't come from a mathematician. It came from a philosopher who happened to be a bishop. George Berkeley, in 1734, published a short and surgical little book called The Analyst, and his point was almost embarrassingly simple. He looked at Newton's derivation and asked one question: is this quantity O0 or isn't it? In the middle of the calculation you treated it as non-zero because that's the only way you could divide by it. Then at the end you set it to 0 so it would conveniently disappear. So which one is it? If it's 0, you divide it by 0. If it isn't 0, you have no business throwing it away at the end. He called them the ghosts of departed quantities. The phrase has stuck for almost 300 years because it's exactly right. In 1734, calculus was producing correct answers, and nobody could defend why. The formulas worked, the reasoning didn't. And mathematicians lived with that gap for nearly a century, because the formulas were too useful to give up, and the foundations were too rotten to trust. The fix took until 1821, and it came from a French mathematician named Augustin Louis Cauchy. His name is pronounced Cauchy. He wrote a textbook for his students at the Polytechnic School in Paris called The Course of Analysis, and in it he did something that, in hindsight, looks obvious and was actually revolutionary. Instead of putting infinitesimals first and trying to make sense of them, he flipped the order. He put the limit first. Any later mention of an infinitesimal was just shorthand for a limit. Here's the line he gave. A variable quantity has a limit L when its successive values approach L so closely that the difference becomes, and stays, as small as one wishes. That last phrase is doing all the work. As small as one wishes. Notice what it does to the argument. You don't have to defend the existence of some mystical infinitely small thing. You just have to show that no matter how close someone demands you get, you can eventually get that close and stay there. The calculus you do after Cauchy looks identical to what Newton and Leibniz did. The same formulas keep coming out the other end. The foundations just stopped crumbling when you leaned on them. Cauchy got the intuition right, but his definition still leaned on English phrases like as small as one wishes, and English phrases aren't proofs. There's a footnote worth knowing here. A Bohemian mathematician, Bernard Bolzano, had already sketched something similar in 1817. His work sat unread for decades. So the credit goes where the influence went, and the influence ran through Berlin a generation later in the lectures of Karl Weierstrass. His name is pronounced V. Weierstrass. Weierstrass stripped Cauchy's idea of every English word and rebuilt it in pure inequalities. He never published the definition himself. It reached the printed page through the lecture notes of his students, especially Eduard Heine in 1872. That version is the one we still teach. Here it is. The limit of f of x as x approaches a equals L if you can win the following game. Your opponent picks a positive number, epsilon, as small as they like. Your job is to come back with a positive number delta, a little window around a, such that whenever x lives inside that window but isn't equal to a itself, f of x sits within epsilon of L. For every challenge, you've got an answer. Let me say the same thing once more in symbols. Because every piece earns its place. For all epsilon greater than 0, there exists delta greater than 0, such that whenever the distance from x to a is positive and less than delta, the distance from f of x to L is less than epsilon. Every theorem in calculus is, somewhere underneath, an epsilon-delta argument. Before we put this definition to work, look at the two ideas hiding inside it. The first one is the thing that always trips people up. A limit describes what a function does near a point, not at the point. The definition forces this by requiring that the absolute value of x minus a be strictly positive. The function might be undefined at a, or it might be defined to some ridiculous value at a that has nothing to do with the rest of the curve. The limit doesn't care. The limit can be a clean, finite, perfectly ordinary number regardless. The second idea is about how x is allowed to approach. It doesn't matter. From the left, from the right, in steady steps, in jagged ones. Any approach to a has to drag the output toward the same L. Both of these ideas come back the moment we start computing real limits, so let's start. In real life, almost nobody actually crawls through the epsilon-delta definition to compute a limit. We use the limit laws, which were proved once from the definition and then stocked on the shelf for everyone else to grab. And the laws themselves say the obvious things. Sums, products, quotients, constant multiples, they all behave the way you'd want them to. The limit of a sum is the sum of the limits, and the same pattern holds for products. Quotients work too, with the obvious caveat that the bottom limit can't be 0, and a constant just slides outside the limit and waits for you there. The one that does most of the heavy lifting in a calculus class, if f is continuous at a, the limit at a is just f of a. You plug in. Polynomials are continuous everywhere. Rational functions are continuous away from their poles. Exponentials, logarithms on their domains, sines, cosines, anything you can build from these, continuous. Most calculus students live entirely inside this regime. They reach for epsilon-delta only when something pathological shows up. Everywhere else, the limit laws do the work. And the reason the laws are trustworthy is the definition we just walked through. The formal definition is the bedrock. The laws are what you actually pick up. I want to do one real epsilon-delta proof before we move on, because until you watch the machinery run, the definition stays abstract. The target, the limit of 3x plus 1, as x tends to 2, equals 7. Geometrically, it's not mysterious. It's a straight line of slope 3 to the point 27, but pretend you don't know that and run the definition. Someone gives you epsilon, some positive number. You need to come back with a delta. Start by writing down the gap between the function value and the proposed limit. The absolute value of 3x plus 1 minus 7 becomes the absolute value of 3x minus 6, which factors as 3 times the absolute value of x minus 2. The gap between f of x and 7 is exactly 3 times the gap between x and 2. So to force the first gap below epsilon, you push the second gap below epsilon over 3. Choose delta equal to epsilon over 3. Now check it. If x is within delta of 2 and not equal to 2, then the absolute value of x minus 2 is positive and less than epsilon over 3, which means the absolute value of 3x plus 1 minus 7 is less than 3 times epsilon over 3, which is epsilon. Done. And that's the move, by the way. Express the output gap as something times the input gap, then choose delta to make the input gap small enough. Every elementary epsilon-delta proof is some version of that. The classic first example. Compute the limit as x approaches 3 of x squared minus 9 over x minus 3. The instinct is to plug in. Plug in x equals 3 and you get 0 over 0, which is undefined. Game over, right? Not quite. Undefined and indeterminate aren't the same word. 0 over 0 is the algebra telling you it hasn't done enough yet. Not that the answer doesn't exist. So do more algebra. The numerator, x squared minus 9, is a difference of squares. It factors as x minus 3 times x plus 3. Look at what happens to the quotient. As long as x is not equal to 3, we can cancel one factor of x minus 3 from the top and the bottom. And this is the whole reason limits were invented to behave the way they do. We are explicitly working away from x equals 3. The definition lets us. Limits only care about what happens near 3, not at 3. So for every x other than 3, the expression is just x plus 3. The limit of x plus 3 as x approaches 3 is 6, so our answer is 6. This is a stranger result than it looks. The original function, x squared minus 9 over x minus 3, is genuinely undefined at x equals 3. The point isn't on the graph, nothing lives there, and yet its limit at 3 is just 6, plain 6. This is exactly the situation Cauchy and Weierstrass were building toward. The limit gives you a way to talk about what a function is trying to do, even at points where the function flat refuses to give an answer. If you don't trust the algebra, check it by hand. Plug in 2.9. The expression equals 5.9, 2.99, 5.99, 3.01, 6.01, 3.1, 6.1. The values crowd in on 6 from both sides. Geometrically, that crowding is the limit. A deeper example next, and a famous one. The limit of sine of x over x as x approaches 0. Plug in 0, you get 0 over 0 again. But this time, there's no clever factoring trick to cancel anything because sine is not a polynomial. We need a different weapon entirely, the squeeze-theorem, and we need a picture. Draw a unit circle. Pick a small positive angle x in radians, somewhere strictly between 0 and pi over 2. 3 areas show up. The first one is a triangle inscribed in the corresponding sector. One vertex at the origin, one on the x-axis at 1, and one on the circle itself. Its area is 1/2 sine of x. The second is the circular sector, the pi slice, with area 1/2 times x. The third is a larger triangle, same base from the origin out to 1, but the far vertex now sits where the ray from the origin through P meets the tangent line to the circle at the point 1, the vertical line x equals 1 at height tangent of x. Base 1, height tangent of x. So the area is 1/2 tangent of x. Quick name for the tool we're about to swing. The squeeze-theorem, if f of x is sandwiched between g of x and h of x near a point A, and g and h both approach the same limit L, then f is forced to approach L as well. The plan is to find two friendly functions that bracket sine x over x and that both head to 1. Geometrically, the smaller triangle sits inside the sector, and the sector sits inside the bigger triangle. So the areas chained together as 1/2 sine x is at most 1/2 x is at most 1/2 tangent x. Multiply everything by 2 to clear the halves. Divide everything by sine x, which is positive in this range. And you land at 1 is at most x, over sine x is at most 1 over cosine x. Take reciprocals on each piece, which flips the inequalities, and you get cosine x is at most sine x over x is at most 1. Now let x tend to 0 from the right. Cosine x tends to cosine 0, which is 1. The constant 1 is already 1. So sine x over x is pinned between two things both converging to 1, which is exactly what the squeeze-theorem needs. The right-hand limit is 1. And sine x over x is an even function. Sine of negative x over negative x is the same as sine x over x. So the left side matches the right side. The two-sided limit equals 1. File this one away. You'll see it again the first day we differentiate sine. Before we close, what does failure look like? Limits don't always exist, and it's worth seeing one that doesn't. Take the function absolute value of x over x. For positive x, that ratio is +1. For negative x, it's -1. So as x approaches 0 from the left, the function is sitting at -1 the whole way. The left-hand limit is -1. As x approaches 0 from the right, the function is sitting at +1. The right-hand limit is +1. They disagree. And now the Weierstrass definition earns its keep. Once epsilon gets small enough, no single number L can be within epsilon of both +1 and -1 simultaneously. So the two-sided limit at 0 doesn't exist. Limits fail other ways too. The function can blow up, f of x tends to infinity. Or it can oscillate harder and harder near a point, the way sine of 1 over x does near 0. The thing the definition gives us in every one of these cases is a precise way to say so. No single L. That precision is what Cauchy and Weierstrass were fighting for. Why did we spend 20 minutes on one definition? Because everything else in this course is a limit in a different costume. Continuity at a point is the statement that the limit equals the value of the function. The derivative is a limit of a difference quotient as the spacing goes to 0. The definite integral is a limit of Riemann sums as you slice the interval finer and finer. Infinite series are limits of partial sums. Improper integrals are the same trick with one of the endpoints chased off to infinity. Even the partial derivatives you'll meet in multivariable are limits, just taken one coordinate at a time. Once you actually understand what a limit is, what Cauchy intuited, and what Weierstrass made airtight, every other definition in this playlist is a special case of it. Where we landed. Newton and Leibniz built calculus on infinitesimals nobody could rigorously define. Bishop Berkeley in the 1730s called them out, correctly. For another century, calculus worked beautifully and nobody could explain why. Cauchy patched the intuition in 1821 by trading the infinitesimal for the phrase, as close as we please. Weierstrass, a generation later, turned that phrase into the modern epsilon-delta definition, and that version is still the one mathematicians use. A limit cares about behavior near a point, not at the point. Two examples carried the idea. The removable indeterminate form, x squared minus 9 over x minus 3, gave a clean limit of 6 at a place where the function isn't even defined. And the geometric squeeze argument gave us the keystone fact that sine of x over x tends to 1 as x goes to 0. Next video, we sharpen all of this with one-sided limits and continuity and start the walk toward the derivative. See you there. Limits are about getting arbitrarily close, and the way this channel gets close to the people who need it is one like, one comment, one share at a time. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.